This lesson is on ocean currents. Major ocean currents. An ocean current is a large volume of water flowing in a certain direction. A lot of times people describe these as like rivers of water within the ocean. So you can kind of think of it like that. It's like a river of water surrounded by water. I know it sounds strange, but that's more or less how ocean currents behave. Wind-driven currents are called surface currents, and they carry warm or cold water horizontally from one side to another across the ocean surface, more or less. Surface currents can extend to as low as 400 meters below the surface, and they move as fast as 62 miles a day. So just keep in mind, they are surface currents, but they're deeper than what we imagine when we just hear the term surface currents. When we hear surface currents, we want to think of like a thin sheet right on the top of the water, but in fact, like the slide says, they can extend to as low as 400 meters below the surface, which is pretty deep when we're thinking about human perception. But in the depth of the entire ocean, it's still what you would consider surface level. Earth's major wind belts, called the prevailing winds, influence the formation of surface currents and the direction in which they move. And the term prevailing winds is a really good term for these winds because they're wind patterns that are predictable and reliable. That's pretty much like, it's patterns that continue to exist, and those are the main influence of the surface currents. All right, the Coriolis effect is the movement of wind and water to the right or left, and it's caused by Earth's rotation. It also influences the movement of the surface currents, and it causes surface currents in the northern hemisphere to move in a clockwise direction and in the southern hemisphere to move in a counterclockwise direction, such as you see in the picture here. You can see here in the northern hemisphere, it's going clockwise, and in the southern hemisphere, our surface currents are flowing counterclockwise. All right, the shapes of continents and other land masses also affect the direction and speed of currents. So currents that are not very close to land masses or continents, they may move slower than, say, part of a ocean current that's moving in a very narrow space between land masses or continents. Those may actually speed up and move faster because they're being more or less squeezed through. So the currents form small or large loops and move at different speeds, just depending on where they are, what land masses they contact or continents they come into contact with. All right, so upwelling is the vertical movement of water towards the ocean's surface. Now, here's where things get a little bit counterintuitive. When we talk about density, and we're going to be talking about density in relationship to ocean currents, but most of the time we talk about density, you already know the hotter material tends to rise while the cooler, more dense material tends to sink. But with upwelling, we have kind of a exception to the rule, you might say. So upwelling occurs when wind blows across the ocean surface and pushes water away from an area, and this allows deeper, colder water to rise up and replace that water that was displaced. So a little bit counterintuitive. In this case, you have some colder water that is more dense that actually has an opportunity to rise. But it's not like the rules of density are being broken necessarily. It's just that this scenario is being created where this water has an opportunity to move into this space. So please don't forget the basic concept of density, because I know this seems to break the rule, but please hold on to what you know about density. Upwelling often occurs right along the coastlines, and it's important because it brings nutrient-rich water from deeper down in the ocean to the ocean's surface, and this helps provide for your smaller, like microorganisms and very tiny organisms in the ocean, which are at the bottom of the food chain and feed the larger organisms. So, like I was saying, this is the one exception where a colder substance is able to rise like a warmer substance normally would. So please don't forget the concept of density. I know this seems to break the rules, and that I know it's going to bother some of you, but It's just one of those things, and those kind of exceptions to the rules do occur in nature. All right, density currents. All right, this is a bit different. These are currents that move water vertically up or down, depending on how dense or not dense certain areas of water are. Okay, so the density currents are a type of vertical current that carries water from the surface to deeper parts of the ocean and back. Density currents are caused by changes in density rather than wind. So the surface currents, yes, they're dictated by the wind patterns, but the density currents are dictated by density, hence the name. So we have two main things affecting ocean water density. The first one is temperature, and the second one is salinity or saltiness, we might call it. So water can become more dense or less dense by a temperature change or a change in the amount of salt it has. So the water can become more dense by getting colder or saltier or a combination of the both of the two, and water can become less dense by getting warmer or less salty. So density currents circulate thermal energy, nutrients, and gases, and they're very important for the same reasons. This helps support ocean life as we know it. All right, impacts of weather and climate. Warm water currents and cold water currents affect weather and climate in different ways. Regions near warm water currents are often warmer and wetter than regions near cold water currents. Regions near cold water currents are often colder and drier than regions near warm water currents. And this just makes sense. Warm air is able to hold more moisture than cold air is. And that's why you get this. That's why you get, like, with warm, you also get wetter, and with cold, you get drier conditions. All right, the Gulf Stream is a warm water current that affects coastal areas of the southeastern United States by transferring lots of thermal energy and moisture to the surrounding air. So you have the Gulf Stream, this ocean current. It comes right by us here in the southeastern United States, and then it goes across the Atlantic towards the United Kingdom. And then over here on the other side of our continent, we have the cold California current, and it comes down from here and brings cold, dry air down along the west coast. All right, the Great Ocean Conveyor Belt. This is the name for a model of the large system of ocean currents that moderates weather and climate by circulating thermal energy around the Earth. So, in other words, the Great Ocean Conveyor Belt is kind of a predictable pattern of our density-driven ocean currents, where you have colder, more dense water sinking, and less dense, warmer, less salty water rising to the surface. So in this model, high salinity water cools and sinks in the North Atlantic, and deep water returns to the surface in the Indian and Pacific Oceans through upwelling and warming. So to sum things up, the global conveyor belt is a deep water current that is driven by differences in temperature and salinity. And again, by salinity, we mean saltiness. So scientists estimate that the Great Ocean Conveyor Belt model takes about 1,000 years to complete a cycle. So you can imagine a deep water current that has to go, through this whole pattern that you see here. So to go one time through probably takes, this one, parcel of water 1,000 years to make the entire trip. So here they're explaining high salinity or very salty water cools and sinks in the North Atlantic, and then deep water returns to the surface in the Indian and Pacific Ocean through the process of upwelling, and that water is warmed and travels along this Great Ocean Conveyor Belt. So one more time, just to talk about the ways that density of ocean water can change. If water gets colder, it will become more dense, or if it gets saltier, it'll become more dense. One of the ways that water can actually cool and get more salty is when warm water evaporates. And you have water that evaporates, and that leaves the salt behind and makes the water that's left behind saltier too. And it cools that water that's left behind a little bit as well. The evaporation does. So that's one of the main ways it can cool off. Ways that water can be heated and become less dense is obviously heat from the sun, or coming in contact with volcanic vents on the ocean floor. Here we have a diagram of the major ocean currents. And you can see most of them have names, and they, you can name them like this because, like I say, they're ongoing and they're predictable. You can observe them, and as you can see here, this is important to note too. Right along the equator, this is the origin of our warm water currents. Okay, and then here at the poles, North and South Pole, that's the origin of our colder water currents. Okay, so keep this in mind as water goes from one of the poles, either the South Pole or the North Pole, and moves toward the equator, it gets warmer as it goes. On the other hand, water that originates at the equator, it moves towards one of the poles, either the North Pole or the South Pole, and gets colder as it goes. Okay, so this is important to note. Water moving from the poles to the equator gets warmer. Any water moving from the equator to one of the poles gets colder. Okay, and you can kind of see that happening. Here we have just a little more simplified version of the same diagram.